Hello everyone. Let's talk about calculus-based electricity and magnetism. We're going to use the Katz book, first edition. You've seen, at least numerous people have seen, when I've talked about non-calculus-based electricity and magnetism, and if you have my classes, either the non-calculus-based class in electricity and magnetism or the calculus-based class in electricity and magnetism, I provide solutions to problems from both types of mathematics, from the non-calculus based and from the calculus based. I give people in my class, my students, I give them the opportunity to look at calculus and non-calculus based problems regardless of the class that they're taking. So, you know, we'll see how much time people have when we want to look at that. But we're working from the Deborah Katz book. We call it the Katz book, first edition, volume 2, chapter 23. And the problems that I'm going to talk about are associated with pages 707 to 712. These problems, 21 from chapter 23, these problems 21, 25, 30, 34, 35, 53, 55, 57, 62, 65, and 79. All of them will scroll, all of those solutions will scroll at the end of the video. I won't do all those problems on film, but all of those solutions will scroll on film from the notes that I have provided for everybody. So what we will try to do to the best of our ability are problems of these problems that are here, problems 30, 34, 35, 53, 55, 57, 65, and 79. So how many problems is that? 8 problems. So we'll see how that works out. Eventually I'll erase this pretty shortly. Let's go to problem number 30. And for problem number 30, they say an electron with charge negative E and mass small m moves in a circular orbit of radius r around a nucleus of charge Z times E, where Z is the atomic number of the nucleus. It tells you how many protons there are. If you multiply Z times E, you'll know that that's the charge. Ignoring the gravitational force between the electron and the nucleus, find an expression in terms of these quantities for the speed of the electron in this orbit. Okay, so basically we're going to say and this is about electric forces, we're going to talk about the electric force and the centripetal force. The centripetal force allowing this sort of motion to take place is itself going to be equal to the electric force. So what you're looking at force electric, force centripetal. Well, the electric force is K Q1 Q2. Well, Q1 is Z times E, and Q2 is E. Don't worry that it's negative. We know it's an attractive force. One's positive, one's negative. Since we know this is an attractive force, the rope is strong enough, the imaginary rope composed of, so to speak, the electric force is going to hold that electron in orbit as it's going. Okay. Divided by R squared. The centripetal force is equal to this. And that's maybe the hardest part of the whole problem. And it's not that hard at all, you guys. So once we get to there, said you gotta have this. FC equals FE. And we know this is the case. If indeed it is the case, and it is, what can you say? Well, let's say solve for V eventually, and find out what's going on at that point. let's solve for v. Well, before we solve for v, let's solve for v squared. Let's multiply by r on each side and divide by m. And when you do that, multiply by r on each side. If you multiply by r on each side, the r squared and the r cancel, and you just got an r on the bottom. And you divide by m. So what do we got? We got kz you have this right here, certainly. Square root both sides. And, you know, there's a lot going on here. Let me just kind of... So I'll be erasing some things as well. Give us a little more room, you guys. But in the meantime, kz the square root of e squared is just e. That'll come out. Everybody else stays underneath the radical. And what we're talking about is here's z. Kz over mr, where E is the magnitude of the electron's charge. You know, talk about the speed in terms of what they've already just told you. And there we go. For problem 34, they talk about a spring system here and figure out what's going on. Number 34, one end of a light spring with force constant K equals 125 newtons per meter is attached to a wall, and the other end to a metal block with charge QA equals 2 microcoulombs on a horizontal frictionless table. A second block with charge Q sub B, negative 3.6 microcoulombs, is brought close to the first block. It's brought close and apparently is being held there in place. So you gotta kind of watch how they say stuff here, guys. The spring stretches as the blocks attract each other so that at equilibrium, the spring stretches as the blocks attract each other so that at equilibrium, the blocks are separated by a distance d equals 12 centimeters. What is the displacement x of the spring? Okay. This is one of those problems that so many problems are like this actually, guys. They tend to be easier done than said, I guess you could say. So let's just actually look at it and see what we can do. All right, let's see what we got here. So what they're trying to say is they tell you the distance
that the blocks are separated at the end of all this process. So, you know, it's kind of interesting how it all goes. The block stretches, the blocks attract each other so that they're at equilibrium. When they're at equilibrium, what's going on? Well, positively charged block right here. QA. And here's a negatively charged block. This is QB. This is still QA. The distance, you want to get the distance between them, you can go from close to wall to close to wall, or from middle to middle, or from far from wall, or from far from wall to far from wall. If the blocks are identical in their dimensions, that's not going to be a problem. That's not going to be a problem. They're telling us that distance is D. It's almost, I don't know, it's almost easier, not easier, who knows. If you'd have gone from how they, because we're saying this, the principle of superposition as well. This is an entire block of charge, so all the charges kind of pull together on this thing. There's a lot you're allowed to kind of assume here. There's Occam's razor, so to speak. What they're trying to say at the end of the day, you guys, is can we please figure out that's X. Can you tell me what that distance X is? How much of a stretch occurred is what they're trying to say. So they kind of went a little bit all over the place with this thing, but it's a pretty simple dynamic in its own right. I mean, the drawing of it's more complicated than the actual solution. Force electric, the electric force, is K, QA, QB over D squared. That's the distance between them. From center to center, from edge to edge, as long as they're symmetric, the distance between them is D. Force that the spring is giving. Don't worry about negative, positive. We know this is negative, that's positive, there's an attractive force. That's it. We know what's going to be drawn toward. There's going to be an attractive force holding these two guys in place where they are, because there is a force associated with the spring pulling in the opposite direction that is equal and opposite to force electric. Well, if we know they're equal and opposite, let's not worry about signs too much. This is the K of the spring. This is the K associated with 1/4 pi epsilon naught. The stretch is X. The real big thing to look at, guys, is the force electric pulls to the right, the spring pulls to the left. They're in a dead heat, so to speak. They're in a tug of war that's actually a stalemate. Force electric equals force associated with the spring. K, QA, QB. And we got that. That's it. I mean, that's the hardest part of the problem, guys. Once you take it to here, the rest is going to be algebra for us. We got to find what X is. To find what x is, divide by ks on each side and you're done. That's the end of the story. Divide by ks on each side. Well, I'll tell you what, let me put the k's together somehow. K over ks. Divide by ks on each side. K over ks times the other business going on here. .99 times 10 to the 9th. 125 is the other one. They said microcoulombs, so that's times 10 to the negative 6. Microcoulombs times 10 to the negative 6. The distance between the blocks, D, is 12 centimeters. Yeah, 12 centimeters is 0.12 meters. We're going to stay with the MKS system of units throughout. It's that simple, guys. What kind of stretch are we talking here? .036 meters. 0.036 meters is the same as 3.6 centimeters. Depending on how they want you to answer it at the end, the way they tell us to answer it, that's how we're going to answer it. Okay, that's the end of it. That answers 34 for us, you guys. Let's go to 35. Two 25-gram copper spheres are placed 75 meters apart. Each copper atom has 25 electrons. Forgive me, each copper atom has 29 electrons. And the molar mass of copper is 63.5463 grams per mole. What fraction of the electrons from the first sphere must be transferred to the second sphere for the net electrostatic force between the spheres to be equal to 100 kilonewtons? So basically, they're telling us that there are two 25-gram copper spheres. They're placed 75 centimeters apart. That's 0.75 meters apart. Each copper atom has 29 electrons, and the molar mass of copper is about 63.5 grams per mole. 63.5463 grams per mole. What fraction of the electrons from the first sphere must be transferred to the second sphere for the net electrostatic force between the spheres to be equal to 100 kilonewtons? 100,000 newtons. It's a great problem. Well, there's a lot there, but at the same time, it should be pretty straightforward for us to do it. All right, let's take a look at it. Number 35. All right, well, it's a lot you can say. Let's try to say a good amount, I guess you could say. They're telling us there's two 25-gram copper spheres. The distance between them is 75 centimeters, which is 0.75 meters. N is the total for each sphere. In other words, how many electrons are present. See if we can figure this thing out. N subtotal, we just call it N maybe, depending how we want to do this stuff, you guys. N subtotal for each sphere. This is just for one sphere, and then the same amount is for the other sphere as far as what's there. I just want to know what's there. Before any transfer takes place, I want to see what's there. Well, they're telling us, I'd like to see how many moles there are. Look, they're making this really simple. Every time there's an atom, there's no real molecule, so to speak, here. These guys are independent of one another, every one of these atoms. There's 29 electrons per atom. Let's just find out how many atoms we have total in the sample. In one of the samples, same amount we have in the other sample, because they're identical spheres, 25 grams each. How many electrons are present with which we can work to talk about electrostatic force and do something? If they're balancing each other out, then nothing's happening. But if there's an imbalance of electrons present, there's going to be a net positive and a net negative, and there's going to be an attractive force equal to 100,000 newtons, 100 kilonewtons, 100,000 newtons. Well, what do you think? Well, it's a 25-gram sphere. 25-gram sphere. How many moles are there in 25 grams? Well, there's 63.54. For every 63.5463 grams of copper, almost looks like a Q, you guys. I don't want to mess this up. Sure it doesn't enough. I'm sure it's close enough, but let's just cover ourselves. Every 63.5463 grams of copper is associated with 1 mole. Well, 25 grams of copper is associated with a fractional amount of 1 mole, because 25 out of 63.5 something is a fractional amount of 63.5 something. So we know it's going to be moles. It ain't going to be a whole mole. If this on top was 63.5463 grams, 63.5463 grams divided by 63.5463 grams is 1. That's 1 mole. This is a fraction of that. I don't know what proportion that would be. I'd say it'd be 40%, 42% of it, so 0.42 moles, something like that. Just off the top of our head. So it ain't a great. It's less than 1 mole. It's a little less than half a mole, to be honest with you. Okay, that's fine. Every mole has 6.022 times 10 to the 23rd atoms. True. That's every mole. Every 1 mole. Yeah, that's how many atoms you'd have, actually, if this was 1 mole. It's not 1 mole. It's a fraction of that. It's about 2/5. It's a little more than 2/5 and less than half. It's less than half a mole and a little more than 2/5 of a mole. Okay, that's how many atoms you got at the end of the whole day. 29 electrons for every single one of those atoms per 1 atom. Per 1 atom. Well, atoms or atom, that's okay. That's they're going to cancel. All right. So at the end of the day, you do this. Total number of electrons for each sphere. 6.87 times 10 to the 24. Yeah, true. That's on each one. Yeah, that's on each one, and they're balanced. They are on each one, so there's no net electrostatic force between them. No net electric force between them. There's got to be some kind of imbalance to happen there to make this thing happen for us. Okay. The N total, you can almost call it just the capital N subtotal. You can almost call it just capital N. But that's neither here nor there. I mean, the big thing here is let's get this thing under control, find out what we're doing here. Well, there's got to be a net force where they're asking us to find a net force. We want there to be a net force, 100,000 newtons. 100 kilonewtons. That's 100,000 newtons. This is 75 centimeters, which is 0.75 meters. 0.75 meters squared. K is what it is. Q1, Q2. Let's see what's going on here. Whatever one of them loses, the other one gains. But the loss of one is a net positive charge equal in magnitude to the net negative charge gained by the other. So whatever happens to one is going to happen to the other. So don't worry. Well, I mean, this may be easier done than said, guys. So what you're going to do is we want to get caught in a situation where N electrons get lost. N electrons get lost. N electrons get gained. Whatever gets lost by one is gained by the other. True. What's going on here? This is just the charge on the electron. This is the charge on the electron. Now you got to be careful here. A loss of this many electrons means it's a positive number. It's a positive charge. A loss of electrons is a net positive charge. A gain of electrons is a net negative charge. Positive, negative, there's an attractive force there. That's what we wanted. So don't worry about the signs as much, just say this. K is K, N number gained, N number lost, and N number gained, N times N is N squared. This one is the charge on the electron. Yes, don't worry about it being negative. The big thing here is it's 1.6 times 10 to the negative 19th coulombs. That's what an electron is. The absence of an electron is an equivalent of 1.6 times 10 to the negative 19th coulombs, but it's a positive, net positive. Losing an electron for one of them means gaining a positive charge in net of 1.6 times 10 to the negative 19 coulombs. The other one, gaining an electron, is gaining a net negative charge of 1.6 times 10 to the negative 19th coulombs. Well, we're not going to worry about a negative answer here. We just know there's going to be a magnitude of force associated with this. R squared is R squared. So I'm not, just the charge on the electron is, I guess, what we're talking about here. If you're talking about this, so just regard this as a positive number. This is really the whole dynamic. If that's really the whole dynamic, we got to find what n is. Small n, right here. Solve for small n squared, then square root it. Well, small n squared is equal to FR squared. Small n squared, I'm going to multiply by r squared on each side and divide by k times the quantity charge on an electron squared. Magnitude of the charge on an electron squared. In plain English, you guys, I'm going to multiply by r squared on each side and divide by It's equal to that. Square root both sides. N is N. F, well, I'll tell you what, there's a lot of ways to write this. I don't know, I wrote it different ways here. If I square root this, the square root of R squared is R. The square root of the charge on the electron squared is just the charge on the electron. So just leave that. Square root of this, yeah, you genuinely can't really get away without the square root being present. And that's it. That's about that. I mean, that's once you get to there, hardest part of the problem. I mean, the setup, once you get to here, the setup should be pretty decent. You get to here, you start making the move you have to make, and eventually that's going to get done for you. So you got this right here, and that's about it. I mean, what you're going to do is your goal is to have 100 kilonewtons, which is 100. Now put it in the MKS system of units. 100 kilonewtons is 100,000 newtons. K is 8.99 times 10 to the 9th. This is 75 centimeters, but use MKS again. Just like here, you made the 100,000 kilonewtons. You made it 100,000 newtons. 100,000 newtons. This is 8.99 times 10 to the 9th. This is 0.75 meters, and this is 1.6 times 10 to the negative 19th coulombs. Plug all that in there, and this will happen for us. I mean, this is where we're going. Once you get to here, you're plugging in all the values. Careful with it. What are they saying? N is the transfer. It's 1.56 1.56 times 10 to the 16th electrons. So, I mean, that's pretty important. So again, you know, what's going on here, right? I think it's pretty basic at that point. You're talking about the fraction, how you want to write it. It's, you know, a lot of symbols here. But N, we said at the end of the day, (1.56 times 10 to the 16th electrons. So (1.56 times 10 to the 16th electrons, and big N total on each one was 6.87 times 10 to the 24th. The fraction, I'll call it F for fraction. Usually, you know, there's numerous symbols you can use. How about small n over capital N subtotal? What does that equal? It equals this divided by that. Plug in, for a small n, plug in 1.56 times 10 to the 16th. For big N, plug in 6.87 times 10 to the 24th. And you don't have to lose a whole lot. Fraction, 2.28 times 10 to the negative 9. What that means is, it means 2.28 divided by 1 billion. 2.28, if you allow me to say that much, as far as like number, it's not really, you want to have a whole, it's got to be an integral piece of the electron, but at least for the ratio, between 2 and 3 electrons, between 2 and, closer to 2, between 2 and 3 electrons, closer to 2, out of 1 billion, get transferred from one to the other. The gain of one was the loss of the other, no more, no less. What the one lost, which was the 1.56 times 10 to the 16th electrons, 1.56 times 10 to the 16th electrons was what was lost by one of the spheres. Yeah, exactly that much was gained by the other sphere. And if they stick on to each other like that, they're not being stolen again, just as they are. If you're going to have that many newtons of force, there's not a huge proportion of it for there to be that great a force, as you can see. Okay? Let's look at 53. They talk about, for number 53, a metal sphere with charge, positive 8 nanocoulombs, is attached to the left-hand end of a non-conducting rod of length L equals 2 meters, capital L equals 2 meters. A second sphere with charge positive 2, a positive charge again, but instead of 8 nanocoulombs, this second one does not have 8 nanocoulombs, it has a positive 2 nanocoulombs. It's fixed on the right-hand end. At what position D along the rod can a charged bead be placed for the bead to be in equilibrium? Well, look, they're both positive, so there's a repulsive force. They're both going to push away from any positive charge. They're both going to try to push to the other one. Each one's going to try to push to the other charge. Each one's going to try to push the positive charge. If you put a positive charge in the middle, each one's going to try to push a positive charge toward the other charge. One's going to push toward the other. Okay, if it's negative, one's going to get if it's a negative charge, each one will try to attract it. So there's going to be either a tug-of-war or a pushing war, but it don't matter as far as location's concerned. The sign just tells you what kind of war there's going to be. If there's a positive bead put in the middle for these positive charges, they're both going to try to out-push each other. If there's a negative charge put in the middle, they're both going to try to out-pull each other. Because the numbers rule the magnitude of what's going on, it won't matter. Whether it's a positive charge or a negative charge, that location where that bead will not move is the same, regardless of whether it's positive or negative. So let's put it together. There's a lot of stuff here, and there's just very much we can say. So let's take a look at it. For number 53. going on? Well, I'll just try to kind of make these look somewhat proportional, I guess you could say. Here's small. This one's plus 2 nanocoulombs. It's very small. This right here is plus 8 nanocoulombs. Also very small, but does happen to be 4 times bigger than this. Notice the units, nanocoulombs, are the same in both instances. So 8 divided by 2 is 4 times bigger. Even if you're not comfortable with nanocoulombs, 8 divided by 2, the nanocoulombs already cancel. 8 divided by 2 is 4 times bigger charge. My gut is telling me, because this is so much bigger, any test charge you put here, positive or negative, and we already explained this, is probably going to go closer to this guy to compensate for the fact that this guy does not have a lot of charge compared to this guy. This guy can hit pretty far away because he's got a lot more charge than this one has. So that's kind of the argument there. Well, I'll tell you what I'm going to do. This whole thing is 2 meters. I'm going to call this distance d of the 2 meters. D amount, it's less than 2 meters, but here's d amount, and this is 2 minus d. And I know this guy we can call charge 1, this guy we can call charge 2, or the scenario here, what kind of electrostatic force does this guy put onto this guy right here? Well, we'll call it F1. The electrostatic force this guy puts on this one right here is F2. If you want this to balance out, regardless of the signs under consideration, F1 equals F2. What does that mean? Well, K is K. K Q1 Q2 over R squared. We know the deal. That's what F is. Well, here, K Q1. This is the test charge Q, or any charge for that matter. We're assuming these guys are rock solid. They're set. They're not going anywhere. What's the distance? We said that guy was D. For the other one, it's 2 nanocoulombs. Again, acting on that Q right there. The distance there true. Ladies and gentlemen, that is the hardest part of this whole problem. If you can bring it to here, if we can visualize everything that we need to visualize. Okay, that's really the hardest part of the problem. As you get to there, you're fine. I'll tell you what, the rest is algebra. If 2 things are equal, if you divide by the same thing on each side, they remain equal. Divide by Q on each side. Yeah, they cancel out. Divide by nanocoulombs, which is 10 to the negative 9. That's 10 to the negative 9 coulombs. 10 to the negative 9, 10 to the negative 9. If this was microcoulombs and this was microcoulombs, this was picocoulombs and picocoulomb, it doesn't matter. Nanocoulombs, nanocoulombs, picocoulombs, picocoulombs, microcoulombs, microcoulombs, millicoulombs, millicoulombs, coulombs, coulombs. As long as we got the same units under consideration, that exponential, that 10 to some power is the same 10 to some power on each side. So you got it to here, guys. When you got it to here, you can divide by nanocoulombs on each side. Divide by Q on each side. What else you want to do? Well, divide by K on each side if you wish. You're going to eventually. What's going on here? Well, I mean, everything canceled out. These are all ones. Eight, 1 times 8 times 1 times 1 is just 8. This is d squared. 1 times 1 times 1 we got this right here. And that's it. And we're gonna solve from there. We're gonna figure out what we're doing here at this point. Forgive me, I should not have said that. 2 was still there. It's gonna go, but it can't go now because that's not the right answer. Okay, so you got it to here. What are you gonna do? Why don't you divide by 2 on each side and multiply by d squared on each side? Many ways you can go at this point, but we're not going to worry about that. We're not going to worry about that. In fact, I did a little, in the notes, I did it a little bit differently. At the end of the day, guys, it ain't going to matter. I mean, you're going to cross multiply, and it's not going to matter. As long as the equation remains an equation, you're okay. You got 4 times the quantity 2 minus d squared. You got 1 times d squared. Yeah, the rest is what we know how to do. I mean, FOIL method, whatever we're going to do, binomial theorem, whatever. We do this, we're getting 4 minus 4d plus d squared. Keep working the math, I guess. 16 minus 16d plus 4d squared equals 1d squared. Minus 16d is plus a negative 16d. Add a negative 1d squared on each side. Add a negative 1d squared on each side. As always, at least in problems like this, it's all math. The rest is math if you get to that point. Here's where we got to go. We got to get to there. Once you get to there, you're going to do the quadratic formula. We know, we already know. I mean, we know a lot of stuff. We know that, ax squared plus bx plus c equals 0. X equals the opposite of b plus or minus the square root of the entire quantity, b squared minus 4ac. The entire quantity on top, including the negative b, is divided by 2a. Absolutely. I mean, that's absolutely the argument. Again, and our gut feeling told us that we're going to be closer to this end. We're not, if we're going to call 1 meter right in the middle, D is going to be longer than 1 meter, and this right here is going to be shorter than 1 meter. As a consequence of all that, they got to add up to 2. Looking at that, D equal, again, it's the same mathematics, guys. Who's what, right? This guy's A, that guy's B, that guy's C. The D plays the role of X. Let's go. The opposite of negative 16, plus or minus the square root of B squared minus 4AC. A is 3, C is 16. I don't want to erase too much, guys, though you do have the feature of going back and looking. And that really, it's not bad. I mean, it's a, you can't really do that live. I mean, so. So you got this over 2A. Okay, it's a mess. But, you know, take a look at it. When you do it, you're going to get, I mean, it gives you kind of two answers here. There's, which is absurd, and the other one is 1 1/3. Yeah, this is absurd. Yeah, it's kind of an interesting, it's a pretty fascinating manner in its own right, I guess you could say. For us, it's absurd. It's got to be between the two places. And we said D is 1 and D is 1.33. So we got, you know, the D that matters is 1 1/3 meters, which is roughly 1.3333. It's an interesting point, at least for what we're trying to do. That 4 would be absurd. You can argue a lot of stuff. Well, first of all, it's got to be between the two. And that's what they're saying here. They're saying, you know, at what position D along the rod, at what position D along the rod can a charged bead be placed for the bead to be at equilibrium? It's along the rod. The rod itself is 2 meters long. So, true. If we're talking 4 meters, from here to here is 2 meters, another 2 meters is 4 meters. Well, yeah, if it's over here and it's positively charged, the positive is pushing it away, and the positive over this positive is pushing it away, and that positive is also pushing it away. So that's absurd. However, if it's negative, you might want to ask the question. It's not on the rod. We said the rod is only 2 meters long, so it's not, but at least from the standpoint of the mathematics, where could there be some kind of validity on this thing? If there is, I don't know. I'm looking at it now kind of for the first time like that. This is your answer. You're done. Because they're saying on the rod, and they're saying the rod is of finite length, 2 meters long. The thing that kind of jumps out at you, don't worry about the nano coulombs, guys. It's pretty fascinating matter here, I guess you could say. If it was over here, we're saying this guy's attractive force. This guy's attractive force. It'd be First of all, if it was positive, they'd both be pushing it that way. If it was negative, they'd both be pulling it that way. So no, it's absurd. It's absurd. However, what if one of these was positive and one of these was negative? Now they're not. They're not. I mean, well, let's say they were. Would it work? Would it be valid to say, you know, let's talk about a distance here. What are you talking about? Well, let's say there's a test charge Q, it's 4 meters away, and there's 8 nanocoulombs here. We don't care about the nanocoulomb. It's all the proportions win the day, and there's a proportion here. Nanocoulombs and nanocoulombs cancel each other out. Test charge Q, and we're saying it's 4 away, 4 meters away from the big one. Let's say this guy is a negative. It doesn't matter if it's positive or negative. One's going to be positive, one's going to be negative. That's not going to matter. Tell you what I'm going to do. This guy's going to be the guy pushing away. So plus 8 nanocoulombs times n. And you know what? It won't matter if it's positive or negative at that point. Won't matter if it's positive or negative at that point. If it were positive outside of here, if there's a negative here, and a positive here, there's an attraction. A negative here and a negative here is a repulsion. So on and so forth. How about positive? Positive and negative here, attraction. Positive and positive, repulsion. It's the same mathematics is going to hold. But this guy would have, one of these guys would have to be of opposite signs. And I'm wondering if it will work, and it may not. I don't, I am kind of doing this completely cold right now, guys. I'm just looking at the numbers. It almost looks like it will. Almost looks like it will. I think I got a feeling it will. The other one is plus. The other one was negative, but I just care about the magnitude of the forces. I just care about the magnitude of the forces, okay? So please note that. You got to kind of be a little careful. One does have to be positive and one's got to be negative. Or one's got to be positive and the other one's got to be negative. And then this one could be anything it wants. And it went over this way. This is K2 nanocoulombs Q. And that's 2 away. 2 away from him, but 4 away from the other. The K's and the Q's go. The nanocoulombs go. This is 8 over 16. I'm wondering if it's going to happen. And this is 2 over 4. We hit the jackpot. Half equals a half. It would work. Perhaps, and that would work. But they'd have to be in opposite signs. Yeah, you're saying, well, wait a minute. So what's your point here? Somehow the signs, the way it would play out, the way the whole thing would play out has to be something of interest. Somehow that works here, because that's the 4, and this is 2 minus 4 is a negative 2. Negative 2 squared would work. So whatever, it's a pretty decent scenario. That's not what happened. Like I said, the answer I gave about 5 minutes ago or so is the answer that's valid because the rod is the length of 2 meters, and it's within those 2 meters that we're talking about. Could you say if the rod was much longer than that, let's say, and they were both fastened, and they're going to fashion something else, and somehow you just change the sign, just a mere change of sign. Have one of them have their sign changed. Have one of them have their sign changed. It works. It works. And we can look at it and the math would go there for us. Okay. But again, that's not what they asked us, so just stay there. This is just a hypothetical situation to kind of look at something. For 55, they say a few very interesting things, and so let's look at it. For number 55, 3 small metallic spheres with identical mass m, each one having identical mass m, and identical charge, each one having charge plus q. So 3 small metallic spheres with identical mass m and identical charge plus q are suspended by light strings from the same point. The left hand and right hand strings have length capital L and make an angle theta with the vertical. What is the value of q in terms of K, G, M, capital L, and theta? Okay, neat problem. Okay, so, you know, it's there for us. Let's see, let's take a look. Let's just take a quick look at it. I think we're okay. Now, I don't know exactly, I mean, we're assuming this guy's a shorter length right here. If there's a tremendous amount of symmetry going on and they're all on the same horizontal level, you got to say that, you know, this guy right here, that's plus, and this guy right here, that's plus. If that's L and that's L, that's got to be shorter than that. They're telling us, again, it's not a good drawing, but suppose it could be a little bit worse. This has mass M. This has mass M, and this has mass M, and they all got positive Q for charge. There's symmetry all over the place here, I guess you could say. What is the value of Q in terms of G, M, M? I'm sorry, what is the value of Q in terms of K, G, M, capital L, and theta, given what we got? I did not put the theta there. Let me do that right here. All right, I mean, it looks good. You know, note, identical situation on both left-hand and right-hand sides. Deal with just one side, and that is fine for solution being found, is what I'm saying. Let's talk more about that in a second. Yeah, that's absolutely true. Look, it's an identical situation, guys, on each side. I mean, it's Q, so how do they write the Q there? Well, I mean, Q will just say it's, positive Q is Q. We're just trying to talk about the magnitude of it. There's an identical situation going on, and this guy's kind of caught between the two, but, so if you can just figure out what's going on here, what side did I use? Let's try to stay consistent. I used the side on the right. So, like I said, you can look at one side of it, guys. So let's take the right side of this thing. And here's the length of that. I never really told you what the length of that was, but I did tell you, or I will tell you. So this is T. There's some tension to the right. And the tension, so he's pulling. Here's this. This is mg straight down. There is a ty component. And there's a tx component. True. If this is theta, this right here is also theta, for whatever that's worth. Alternate interior angles are congruent. This is 90 minus theta right here. I don't even know that we need to go there. One thing I should have maybe been a little more cautious about. All right, I'll tell you what. I mean, there's a lot going on here. The ty and the ty and the mg are equal and opposite to each other. The tx is pulling this way, and there's an electrostatic force going this way. Now I'm going a little differently from my notes here, guys, but the notes that I wrote earlier at some earlier time agree 100% with this. It's not going to be an issue. What's going on? Well, I mean, it's a pretty fascinating point in its own right. I mean, you could say that. That's a very important point. First of all, this is a true statement, but man, it's a loaded statement, I guess you could say. What's going on here? This guy at a distance, I don't think they gave us a distance there, guys. No big deal. We'll get the distance. Does everybody understand? This right here is equal to, here's theta. This is big L right here. And this is big L right here. This right here is L sine theta. This right here is also capital L sine theta. That is this length right here. That is this length right here, and the whole length from way over here all the way to here is double this. It's L sine theta plus L sine theta, or 2L sine theta. What's going on here? Well, the electrostatic force is repelling this guy that way. What do you got? You got Q, you got Q, you got KQQ over R squared, and R squared is L sine theta. The quantity L sine theta squared. That's one of them. The principle of superposition, you're right here, this guy will also punch it that way. It's going to be KQQ again over R sub F squared. r far away squared, which is r far away is L sine theta plus L sine theta, 2L sine theta. It's the quantity 2L sine theta squared. Both of those contribute to the FE right here. And the TX has to be equal and opposite to hold him under control. The TY has got to be equal and opposite to this one to hold it under control. So you got this and this. You got this and this. And that's going to get you there. At the end of all that, that's going to get you there. Okay, so what do we got? I mean, well, let's see what we got here, guys. I mean, this is kind of a weird, you got to be careful with what we got right here, I guess what you can say. If this is, you know, the T, and this is the TX, and this is the TY, well, the TY is, you know, I don't want to draw it again, but let me draw it over to the side, I guess. If this is T, and this is TX, and this is TY, and that right there is theta. TY divided by T is cosine theta. TY is T sine theta. And TX forgive me, cosine theta, right? Okay, I'm sorry. Let's make it long story short, I guess. TY divided by T TY, you know, TY divided by T is cosine theta. And for the other one, TX divided by T is sine theta. TX is T sine theta. TY is T cosine theta. All right, there it is. You got this. Let's, you know, again, guys, we're so used to the x components being associated with cosine, and we're so used to the y components being associated with sine. Yeah, I get it, but the math is the math, so we deal with what we're going to deal with. If you want to make it associated with cosine, then it's going to be the cosine of 90 minus theta. If you want to make it associated with sine, then it's going to be the sine of 90 minus theta. Let's not go there, but we can do it. You know, there's a lot we can do here. The big thing here is this. The net electric force, T sub x equals T sub y, forgive me, T sub x equals F sub e. So what we can do there is, this guy pulling that way is equal and opposite to the two situations. The far away is this. Q, and Q. KQQ over R squared is KQ squared over L sine theta plus L sine theta, which is 2L sine theta, the quantity 2L sine theta squared. That's the far one. The close one is the same exact thing, KQ squared over, except for the R. KQ squared over the quantity L sine theta squared. So, Tx is the pull that way. Tx the pull that way equals Fe the push the opposite direction. So Tx pulls that way, Fe pushes toward the opposite direction. You want it to be at equilibrium. So Tx holds the electric force in check. Tx is equal to KQ squared over the long distance squared plus KQ squared over the short distance squared. And the same exact thing is happening on the other side. So if I just solve for one side, I've got this thing under control. Ty and mg are equal at opposite forces. Ty pulls up as much as mg pulls down. Period. So we got that right there, guys. So let's see what we can say here. If you actually do all this, this becomes 4L squared sine squared. This becomes 1L squared sine squared. You've got to get common denominators and all other stuff to work for us. So let me see what I want to erase. The big stuff we got. So I think we're doing good. And again, you can always come right back to this stuff. We should be okay. What happens is, for the Tx, you got KQ squared. You square all that bottom stuff. Got the same thing up here. Down here you got something really close to it, but it's off by, off by a factor of 4. Multiply on this side, right here, multiply by a special 1 called 4 over 4, and you end up getting multiply by a special 1 called 4 over 4. So you can be right here, 4 over 4. Four right here. Well, you see why I did that. Add them together. True. Okay. We got that. We've got the ty. Ty is t cosine theta, right? T cosine theta is ty. You got the mg right here. So, and you're trying to find the end of the day here, trying to find out what you're going to call Q. What is the value of Q in terms of that? So you got this right here. Okay, so got a lot of stuff here, guys, that we did. So we look at this, and we're going to try to find where Q would be. But notice I brought tension into the whole thing, and which is fine, absolutely helps. Brought tension into the whole thing, but what can we say about it? Well, I think we can say an awful lot about it because they don't have it. We can solve a lot and talk about a lot by bringing tension into this whole thing. However, there's the issue, they don't want tension in the final solution here. I think we can do okay. In the final solution to this problem, they don't want tension. But we brought tension into it because it's a physical reality, and we can do a lot of mathematics with that physical reality. We did a lot of mathematics with it, and we're almost there, believe it or not. I mean, what's going on is essentially this. If I'm looking at, if we're looking at t sub y looking like this, and you want to write it looking like right, and that's really what that is. And we did all this. Let's talk. We solved for t sub x. We did all this. We did t sub x equals kx squared over the quantity 2L sine theta squared plus kx squared over the quantity L sine theta squared. We added them together, we got all this over here. Didn't we say that t sub x, that way is t times the sine of theta. So t sub x is t times the sine of theta. And so what we got here? So we got t times the sine of theta. The other one is t cosine theta, which is equal to mg. Wait a minute, there's equations all over the place here, guys. If this equals that, and this equals that, why don't you divide this by this, and divide that by that? And you're all set. So we got this right here. Sine theta over cosine theta equals, there's a lot there, but there's no t there, and that's a good thing. You got 5 q squared over 4mg over 4mg L squared sine squared theta. Sine theta divided by cosine theta is tan theta. Yeah. There's a lot to say, and like I say, I did a lot of stuff with this. Let me just make sure there's many ways to write this. Let's just see we're writing it the way they want us to write it. Yeah, it's basically the same argument. So what you're going to do here is you're going to get q squared by itself by multiplying by 4mg L squared sine squared theta on each side and divided by 5k. 4mg L squared sine squared theta times tan theta divided by 5k. Square root both sides, and it works on both sides. Guys, I'm probably going to erase this. It works, whatever's going on here is also going on here. So that's fine. If you can analyze the situation here between Q and Q, see, this is the important thing. There's Q and Q, but there's a third Q, and we brought them in there to make sure that this was happening that way. The far off Q does hit that one. Not with as much electric force as this does, but it does hit it, and we have accounted for it. Over here, this becomes the far off Q hitting this guy, and this is the closer one. This is the closer one in both instances. The far off one is this guy when dealing with him, and the far off one is this other one when dealing with that one. So whatever, that's fine. That works. That works. So we got the whole thing set up. I mean, the whole thing works. We got to here. We got all that. What we have is see what we got. Square root both sides. That thing in blue. Square root of Q squared. Square root of Q squared is Q. Square root of 4 is 2. Square root of L squared is L. Square root of sine squared is sine. So square root of 4 is 2. Square root of L squared is L. Square root of sine squared is sine. Everybody else is legitimately square rooted, I guess you could say. So the 2, the L, and the sine theta That's it. Again, writing it out is more difficult than I guess even thinking it out. You can you get the whole process where eventually you're gonna go. You got all this, okay, well, there's a t sine theta here, there's a t cosine theta here, a t sine theta here, a t cosine theta there. T sine theta divided by t sine theta divided by t cosine theta is tan theta. Tan theta equals the ratio of these two. And the rest you just play the game and you're fine. Let's make sure that's all they had. That's all we had on that, guys. So it's looking pretty good. Okay, as we said, it was a square root right there, guys. You know, great big square root with all this stuff underneath it. And you're there, and then you multiply with all that. So it's looking pretty good. Let's look at 57. 57, how many electrons are in a 1 gram electrically neutral steel paperclip? The molar mass of steel is approximately that of iron, or 55.845 grams per mole, and a neutral iron atom has 26 electrons. All right, pretty simple. I mean, based on stuff we've done in the past, we kind of solved this type of problem already, and it was already, when we had solved this type of problem already, it was within the context of a more complicated problem. So let's see what we can do. All right, so for 57, guys, as we said, how many electrons are going to be in that 1 gram electrically neutral steel paperclip if the molar mass of steel is approximately that of iron, which is 55.845 grams per mole, and a neutral iron atom has 26 electrons. Pretty easy, guys. Like I said, we already did this within the context of a more complicated problem. So this should be pretty easy for us. Basically, you can do a lot of stuff here, I guess you could say. If you're talking about 1 gram of a substance, and there is 1 mole associated with 55.845 grams of the same substance. Every 55.845 grams is associated with 1 mole. Well, 1 gram is going to be a lot less. 1 gram is going to be a lot less than 1 mole because you need 55.845 grams. 55.845 grams for every mole. Well, 1 gram is a fraction of that. It's 1 over. It's actually 1 over 55.845 grams to tell you how many moles that is. Well, of those moles, that fraction of a mole, if it were a full mole, it'd be 6.022 times 10 to the 23 atoms for every 1 mole. Well, we just said it ain't going to be 1 mole. For it to be 1 mole, it would have to be 55.845 grams. If you had 55.845 grams of iron or steel, the way they're saying it, the way they're proposing this, if you had 55.845 grams of steel, that's 1 mole of atoms present. 1 gram, that's a fraction of it. It's 1 over 55.845 grams. It's 1 gram divided by 55.845 grams. It's 1 divided by 55. It's less than 2% of a mole. It's less than 1 out of 55. And that's less than 2%. That's less than 1 out of 50. Well, okay, if there's about 1/50th of a mole, and every mole's got this many atoms, you got 1/50th this number of atoms. And every one of those atoms, when it's neutral, has 26 electrons for every one of those atoms. And you can think it out, you can think it out the way you want to think it out and explain it to yourself the way you want to explain it, but the argument's got to go somewhere along these lines. But the way you're most comfortable saying it, that's understandable. Go for it that way. When you actually do this, you're talking about 2.8 times 10 to the 23rd electrons. And that's it. And that's 57. 65, they're going along the same lines, playing a game we played not long ago at all. We talked about those metallic spheres. They're kind of doing it again here for problem number 65. There is a drawing that shows 2 identical conducting spheres, each with charge Q, suspended from light strings of length L. If the equilibrium angle of the strings If the equilibrium angle the string makes with the vertical is theta, what is the mass of the spheres? What is the mass m of the spheres? So, similar type of argument in regard to that. So let's look at number 65. So what's going on? And they want you to know what, given what they've said to you, are you able to talk about the mass? Are you able to give, very similar to what we already did, was that problem 55. Very similar to what we did with 55, you guys. Somewhat similar argument, a little more, in some regards, somewhat easier, actually. Okay, they're telling us that's L, that's L. Let's see here, guys. Right, and the way I've drawn this a little more exaggerated than from what they've drawn it. They're telling us that each one, they're both positive, and each with, shows two identical conducting spheres with charge Q, suspended from, they're probably saying net charge Q. So in other words, they're saying positive, so we'll say positive. I mean, so they both got Q. And that's about it. And we get kind of caught in very similar circumstances that we've been caught in the past, you guys. If you look at one side or the other, there's identical phenomenon going on. So if I just solve for one side, I'll be fine. I have to account for both things. Remember, when we did problem number 55, yeah, if I solved for one side, I was fine. With problem number 55, if I solved for just one side, I was fine. Yeah, but what did I have to do? I had to take into account all three identical spheres to set up the mathematics. Whether I went to one side or the other, it's an identical situation on each of those sides. Either in both of those sides, in each of those sides, whatever you want to say. On one side or the other, both situations, each one of those two situations are identical one to the other mathematically as to what's going on. But I had to use everybody that was there. I had to do some long distance repulsion and some up close repulsion added together. That gave me the total repulsion that was going on one side of the equation, on one side of the geometric reality that was being shown to me. On the other side, on the opposite side of the geometric reality that was shown to me, the same exact phenomenon hold. So the mathematics were good either way. They would work very well either way. So let me think. I mean, the way we want to look at it, you could say that I saw how I drew it. I just don't like the way I drew it myself, to be honest with you, in the notes, guys. Let me, I guess, take a snapshot of it, and just say, hey, look, let me just take that one thing that's there, and let's talk. There is, right here, there's repulsion. I'm just taking one side now, guys. Okay, let me think here. There's a tension here, T, and there's a T sub y right here, and there's a T sub x right here. There's theta right here. Alternate interior angles are congruent. And it's looking something like that. Not a great drawing, but alternate interior angles congruent. There's theta. Ty, Ty is T cosine theta. Tx is T sine theta. This is starting to look familiar already. So what's going on here? Well, the Tx is identical to F sub E. And the Ty, equal in magnitude at least, is Ty is equal in magnitude to Mg. So, period. I mean, it's the end of the story on that one. So how does that work? Well, pretty straightforward on that one, because what happens is you got, this is L, that distance right there is L sine theta. That's L, and this guy is L sine theta. L sine theta for this guy, L sine theta for that guy. That's together, the distance between them is 2L sine theta. What we have is, well, we just said it. I mean, Tx equals Fe and Ty equals mg. Whereas, it's good enough. I mean, so we look at it like that. Tx T sine theta, Fe is KQQ, KQQ is KQ squared. KQQ is KQ squared. True. Not true, actually. It should be two of them, right? We said it was L sine theta plus L sine theta, or 2 times L sine theta. That's that. That's Tx. Ty. Ty is T cosine theta. Again, it's a we're so used to x components being associated with cosine and y components being associated with sine. But if you do set it up, the x component has got to go this way. It's the same as this, right? And that's opposite of this. So it's T sine theta will give you the Tx. And T cosine theta will give you the Ty. So the Tx is T sine theta. The Ty is T cosine theta. And the Ty, T cosine theta, is equal and opposite to mg. Simple as that. I mean, the Ty was the mg. When you're looking at this, here's Tx, here's Ty, you're good to go. Now the question they're asking is, I think they're asking here, if the equilibrium, what is the mass of the spheres? They want you to solve for mass. Look, it doesn't matter a whole lot, guys. Once you get down to here, you've done a lot. Go T sine theta, T sine theta, T cosine theta. This equals that. This equals that. This divided by this is the same as that divided by that. T sine theta divided by T cosine theta is sine theta over cosine theta. And we know how that ends too. KQ squared over mg. We'll square them, right? 4L squared right. Well, yeah, I mean, we know that's tan of theta. I mean, so tan theta is kq squared True. What do you say? You know, there's a lot you could do here. What do you say you multiply on both sides by m and divide by tan theta on both sides? You should be okay. We'll see how I actually did it. So basically what I did, guys, so many ways to go, but I'll tell you what. Just multiply by m on each side and divide by tan theta on each side, and you're fine. Yeah, I mean, there's, I suppose, a number of ways this can be written. It's not really a big deal. That's fine. Actually, I don't think anybody's going to have a big deal, kind of big issue here. But at the end of the day, there's a number of ways to write it. Let's put the tan, I think I put the tan theta in front, more in front than the sine squared theta. And that should be it. Okay, fantastic, guys. It looks good. That was 65. This is the last problem in this set. The last problem in this set is problem number 79. Problem 79, two positive charges, each with charge, so two positive charges, each with charge capital Q, are held at positions x equals negative a and x equals positive a along the x-axis of a coordinate system. A small sphere of mass m, small m, and positive charge, small q, is placed at the origin, but it can move freely back and forth on the x-axis. Show that if the sphere is displaced by an amount x, which is much less than a, and released, it will undergo simple harmonic motion about the origin with angular frequency given by omega equals the square root of the quantity 4k capital Q small q, the entire quantity divided by ma cubed. Then that entire quantity square rooted. Okay, this is, again, easier done than said, guys, when we're doing it. Let's take a look at what we know regarding simple harmonic motion and then kind of apply that and look at what we have here. Well, let's see here. I guess you got to pretend this thing was a spring in some regard. Exactly how we'd want to look at this thing. Let's look at some of the mathematics. Well, here we are, and we got a charge here. These guys are held in place. It's capital Q and capital Q. There's a small q right here. You're going to displace it a distance x, which is a lot smaller than this guy goes to guy goes from 0. This goes from 0 to negative a. That distance is a. From 0 to negative a, that's a distance of a. And this is also a distance of a from 0 to a. True. The mass itself is mass small m. They're claiming this little x is really little compared to a. There is a resultant force on this. When you, now the way they're saying this, I mean, they're kind of, let's just speak their language, I guess. There's two positive charges. There's two positive charges, each with charge capital Q, and there's a positive charge small q. So what happens is if you displace this guy one way or the other, the very fact that you displaced it, you're kind of giving an advantage. Look, there's perfect equilibrium if you're right in the middle. But if you displace it just a little bit, one of the charges, one of the capital Q's has an upper hand. One of the charges, capital Q, has the upper hand in the whole situation. So the one that's once you get closer to one of them, the one to which you are closer has more force than the other one. So it's kind of like he's going to push it back. So it's going to oscillate back and forth, and we think it's going to do simple harmonic motion if x is a small number. The resultant force is a tug of war. The tug of war is a dead heat if you're right in the middle. The distance is a from one of the q's, and the distance is also a from the other q, and k capital Q small q over a squared equals k capital Q small q over a squared. Nobody's moving. But if you displace it a little bit, one of the charge to which you are closer gains the upper hand and pushes harder right back. And this thing will go back and forth like it's a spring in simple harmonic motion. That's what we're claiming. That's what we think will happen. Once you get closer, if you were like to pull it this way, for example, pull it this way. Well, now it's not a distance, it's a minus x. So it becomes, this guy wins it. And the other one's further away. One guy's pushing back. He's pushing back this way. He's pushing, whatever you want to say, however you want to do it. Don't worry about positive or negative. This stuff just alternates. It's going back and forth. Let's just see what the force is. Let's get a positive answer to the force. It is a restoring force, so technically you can say it's negative the way F equals Kx, K spring, right? K sub S for spring. F equals negative K sub S x. F equals negative Kx, K being the spring constant. Okay. For now, let's not go there. Let's not worry about that as much. I mean, maybe if we're going to do that, doesn't matter. You can go this way or you can go that way. That's not the big deal. The big deal is if you take this guy and go that way, you are a minus x away from him. More force than this guy has, because this one's got a plus x distance. This guy wins by how much? Not by a lot, but they do win. There is a victory there. That's the resultant force. Whenever you displace it, you're talking about the force being that. Well, how can we do that? Well, there's a lot you can do. You can multiply. There's a whole lot you can do, I guess you could say. When you look at something like this, just want to see how I want to exactly argue this thing. All right, let's multiply this guy by a special one called the quantity a plus x squared, the quantity a plus x squared over the quantity a plus x squared. Here, you're going to multiply by a special one called the quantity a minus x squared over a minus x squared. You're trying to get a common denominator. Well, multiply the two denominators together, you got a common denominator. Then just do the special one, the quantity a plus x squared over the quantity a plus x squared. The quantity a minus x squared over the quantity a minus x squared. Absolutely. So what happens is, yeah, okay. It's basically what I had said is going to happen is going to happen. What's going on here? Look, let's try to make it easy. K capital Q small q. So you got K capital Q small q. K capital Q small q. You got all the bottom stuff, and then you're subtracting the other stuff. So the FR is K capital Q I'll leave that, and then I'm going to do this. That's the quantity a plus x squared minus the quantity a minus x squared. True. Guys, this is a squared plus 2ax plus x squared. This is a squared minus 2ax plus x squared. The a squared and the a squared, when subtracted, are gone. The a squared and the a squared, when subtracted, are gone. The x squared and the x squared, when subtracted, are gone. The 2ax minus negative 2ax is 4ax. That's where they're getting that. True. I mean, I wrote it in a little different order in the notes, but that's absolutely true. See what we want to say here. Yeah, it's a true story. Look, guys, we've been saying this from the beginning of the problem. X is very, very small. X is very, very small. So there's a lot going on here. A lot of ways you could play this. I guess I'm debating here how I want to do it. You could do a bunch of stuff here. Let me kind of go off away from the notes just for a second, just if you want to believe this. Squared, huh? They're both squared. You know what that's the same as? Both squared yeah, if you bring the square inside, you get the quantity a plus x squared. If you bring the 2 inside, you get the quantity a plus x squared. Bring the 2 inside over here as well, you get the quantity a minus x squared. Okay, you do this right here, you get a squared minus x squared, and then you're squaring that. The argument, you know, there's probably a number of ways to do this. Once we get to this point, I guess. And I'm going a little bit off the... You actually do this, you get a to the 4th minus minus 2a squared x squared plus x to the 4th. The argument here, you know, there's a lot you can say. The argument here is x is very, very small. So when you square it, it's even smaller. When we say small, we mean very, very small in the number system in which we're working in relation to x. If you wanted to see what you could say here regarding this stuff, a would be really huge and x would not be that big at all. And you could kind of look at it. We could say x squared to a squared minus x squared. You know, you're basically talking about this, but it's smaller, but really this entire quantity is smaller than 2a squared. But you multiply it by this, it's trivial compared to how big a squared is. You know, you're talking about how much bigger one is than the other. And there's a lot of ways we can kind of look at it, but you can kind of look at it as this right here and how would it compare to the other thing. I mean, you could say, how does this compare? 2a squared minus x squared is a particular number. It's actually smaller than 2a squared. Okay. Well, if it's smaller than 2a squared, let's use 2a squared just to be safe. 2a squared x squared divided by a to the fourth. Let's see what kind of ratio you get. 2a squared x squared right, 2a squared x squared, and actually this is, you're not even taking away that much because you're gaining some here with the x to the fourth, divided by a to the fourth. What happens here is you get 2x squared over a squared is what you get, because the a squared and a to the fourth cancel, and you end up getting 2x over a x over a. X is tiny compared to a. X is tiny compared to a. If this is 1 over a million, and this is 1 over a million also, 1 over a million times 1 over a million is 1 over 10 to the 12th. It's really tiny. So that's the justification for why something like that would happen. And that's how much is being taken away. And it ain't a whole lot being taken away from there. And in fact, even this small amount, even this minuscule amount, isn't the amount being taken away, because you also got this to here. So it's just, it's something, it's definitely smaller. I mean, 2a squared, you know, a squared is bigger than x squared. So it's going to be a net takeaway. But man, it ain't much. I mean, you're getting this right here is definitely bigger than this right here. So it's a positive number. So it's a positive takeaway, but even if you ignore this guy right here, this really makes things really small. This really makes things really small. And this shows it. If this is tiny, 1 over something huge times 1 over something huge is 1 over something huge squared. It's even more tiny. And so basically what they're trying to say when you're doing all this, what they're trying to say with that is this is roughly equal to, when that happens, and this is more of an explanation that I gave, I think it's more of an explanation. I haven't looked too far ahead in the notes. It's been a while since I wrote the notes, but to make a long story short, our suspicion's confirmed. You are losing something. You're definitely getting something taken away. Kind of look at it. Let me try to think about how I wanted to say that. Right, you're getting something taken away, but man, it sure ain't a whole lot. It sure ain't a whole lot. You saw me mess with it. There's very little being taken away. And so it's going to be, let's not get this wrong here. This right here, this product right here, is definitely something, based on what you just saw me do, is definitely something that's smaller than a to the fourth. This thing comes close to a to the fourth, but it's a little bit smaller. It's a little bit smaller. It's a little bit smaller than that. You got you got a squared times a squared is the a to the fourth, whereas with this guy, you got the a plus x. See how we could actually say that. We could look at it as, what did we say it was when we actually did it? We played that game. We got a squared minus x squared, a squared minus x squared, and the other one was, forgive me, no, it was as simple as that actually. It was a squared minus x. So we did this, we pulled it out, so we said we had this, a minus x. Great, that's a difference of two squares, and you're squaring it. You can do that, and it comes out the same thing. Well, we said this, so it's going to be smaller, but man, not much. Not much. Not much. You know, you're looking at a situation where it just didn't come out to that. It just didn't come out to being too much of a difference on that, guys. We ended up doing it. We got a to the fourth, right? A to the fourth minus 2a squared x squared. So we got a to the fourth minus 2a squared x squared plus x to the fourth. Wow, you're already gaining. You got this, and that's positive, whereas this right here is some negative. Yeah, but it ain't a whole lot. I mean, definitely this one is more negative than that one's positive. But let's say you're losing a total of 2a squared over x squared, as we said. So 2a squared over x squared is what you're losing, compared to, you know, so that it's less by that amount. What are you talking about? Well, you're talking about roughly a to the fourth minus 2 a squared x squared plus something. So you're not even losing this much because you got a plus x to the fourth. So I'm claiming I'm losing even more than I'm actually losing, because then I'm gaining x to the fourth, which is still absolute value-wise smaller than this. But so I'm still losing something, but I'm not losing as much as this, but I'm claiming I'm losing as much as this. You know, how close are they to one another then? You know, if you got a to the fourth like this, how far off? What's the percentage error on that? Well, a to the fourth goes into a to the fourth one time. Goes into here, and we said 2x squared over a squared. Well, we just said x compared to a. X compared to a is minuscule compared to a. Something very small divided by something very big is very, very small indeed. You square it, it's even smaller. You know, you multiply by 2. Yeah, okay, fine. It's still tiny. I mean, it's not like it's 1 over a million multiplied by 2. It's 1 over a million squared, which is 1 over a trillion times 2. Well, 2 over a trillion is 1 over half a trillion. Well, 1 over half a trillion, man, 1 over half a trillion is sure a lot more. The 2 makes it more. I get that. I get it. It doubles it. But if this is tiny, like 1 over a million, 1 over a million, the quantity 1 over a million squared is 1 over a trillion. You can double that if you want, but you're still, you know, that's 2 over a trillion. That's 1 over half a trillion. That's 1 over 500 billion. Man, that's a lot more than 1 over 500 billion is a lot more than 1 over a million, and they're both really small. So I just want to, forgive me for kind of beating this thing up a little bit, guys, but when they're saying they're about equal, when you're about to see what I'm saying, it's not something they're just throwing at us randomly. I mean, it's a valid argument. So if you're going to do that, well, we just said that. We said it's a good approximation. This thing right here is approximately equal to 4ax kq over q. Well, again, you do not want to see that song and dance again, nor do I. You know what that comes out to. It's pretty darn close. Pretty darn close to that. And that's a big thing. That's a big thing. Yeah, if it's a big thing, what do you got to say? Well, look at the A. Look at the A. This is a to the 1. This is a to the 4th. This right here becomes 4x k q q over a to the 3rd in regard to that. Approximately here, but that approximation is exactly, the approximation is exactly equal to, it's exactly equal to that. All right. This is always a restoring, guys, when we do this little tug of war here, if I pull this guy this way, this guy's going to push him back. And when he gets back far enough, this guy's going to say enough is enough. Now I got more power, I'm going to push you back this way. Then this guy's going to say the exact same thing, and it's going to go back and forth. It's going to oscillate in what we think is simple harmonic motion. It's going to behave like a spring, is what we think. So, okay, let's see what we got. Approximations all over the place, but they're reasonable approximations. I just told you that. I put some big numbers in there, and when I squared, I put 1 over a big number, and when I squared 1 over a big number, I got something incredibly minuscule. Multiplying by 2 ain't changing it. Why is it not changing it? Because you're not multiplying by 2, you know, it's not, yeah, you're multiplying by 2 on top, but it's not like you're, you know, it's not like you're multiplying by 1 billion on top, you're multiplying just by 2. On the bottom, you've multiplied by 1 billion twice, or by 1 million twice, or whatever. 2 compared to 1 million, it's not going to cut it. Not going to cut it. So you're looking at this stuff, you guys. This is always a restoring force, guys. I just wrote it a different way. I put the X kind of on the tail end of this thing, kind of make it look like, it looks like a K, doesn't it? I mean, here's an X, that looks like K, and here's F. F equals Kx. Now this force is always a restoring force. And if X is, you know, this force, Fr equals 4K capital Q small q over a squared, all of that times x, is always a restoring force. And if x is a magnitude x greater than 0, then this is a magnitude of that restoring force. This thing right here. If it's less than 0, then it's going the other. This just gives you direction, guys, if you're going to put signs in there. So if x is allowed to be plus or minus, which indeed is what happens, then we'll indeed describe the magnitude and direction of the restoring force. So basically, guys, this is just telling you what happens with the first push. How is this guy pushing back? If you've taken him to a maximum displacement or any displacement, what kind of a force is happening? Yeah, it's that. Now, if you pulled this thing in the positive direction, the net force wants to take you negative. If you take this thing in the negative direction, the net force wants to take you positive. If you pull it in the positive direction, the resultant wants to throw you in the negative direction. If you take it, so if you move this in the positive direction, the restoring force wants to get you back in the negative direction. If you pull this in the negative direction, the restoring force wants to get you back to the positive direction. For that reason, they put a negative there. So, Fr equals negative 4 K capital Q small q over a cubed times x. That looks a lot like K sigma of a spring times x. Yes? You know where I'm going with this, guys. You guys know where I'm going with this. Forgive me. It's got to be negative. It's a restoring force, right? This guy right here and this guy right here, or if you want to circle both negatives, that's fine. If two negatives are equal, their positive counterparts are equal. There it is. That's the big thing right there. I mean, so you go here. You got it. I mean, the K spring, because I don't want to confuse the K with, we're doing Coulomb's law and stuff, right? So let's call it KS, K spring. K spring equals 4 K Q over A cubed. True. Also true. Omega is Ks over M. Whoever behaves like that spring we'll call Ks. Well, I think we established who behaves like that spring. There's a restorative force there. This thing can't go forever. You understand, you pull this thing back just a little bit, it's going to fight back just a little bit. But by the time it gets over there, it's going to get stopped. It's going to get stopped. It's going to get to its equilibrium position, but it's going to come right back and finish where it started. From conservation of energy, the work that you did there, it's a pretty fascinating question in its own right, isn't it? I mean, how much work is being done to actually do this, right? And where's it going to go? Well, it can't be any more work than, you realize when you do a spring, you guys, if you were to pull it, and if this were just truly a spring, if you pull it over X, how much work did you do? You did 1/2 kx squared work to pull it that far. When you let it go, in the middle, it's going to have all that pull that you did, all that work that you did, all that work in the middle, all that work that you did is going to show up right here at the former equilibrium point, or at the equilibrium point. It's going to show all that work that you did is going to show up right here at the equilibrium point, but it's not going to have any potential energy of the spring. It's going to be all kinetic energy. All that kinetic energy is going to go over and get stored as potential energy again. Oh yeah, 1/2 kx squared. What does that mean? It went the same distance x. The same thing with this thing. When you pull this thing over, when you pull this charged particle over, ladies and gentlemen, you've done work. How much work? Well, that's another story, the work you did. There's a resultant force, and that resultant force, I guess if you integrate it, here it is. What am I talking about? Here is the resultant force. Here's the resultant force. We don't have to worry about negatives right now. Let's just look at magnitude of what's going on. But there's the negative for bookkeeping, the negatives there. 4K, capital Q, small q, and A cubed are all constants. And really, yeah, they look like it to me. Coulomb's law, Coulomb's constant, not Ks for a spring, but Coulomb's constant. That's a constant. K's a constant, 4's a constant, capital Q's a constant, small q's a constant, and A cube's a constant. That's a constant. If I pull this thing x away, if I pull this thing from here to here, x away, I stored energy 1/2 We'll call it capital K. We'll call this real big thing. We'll call this real big thing capital K. Or we can just call it KS, the imaginary, the thing that behaves like it's a spring. We'll call it the KS. I don't want to say it behaves like it's the spring. Well, if this behaves like it's a spring, sure does, that's a constant. 4K, capital Q, small q, and A cubed, they're all constants. That's a constant too. If you take out the X here, you might as well call it capital K if you want. If we're not comfortable doing any of this stuff, we'll call we call it capital K, for the, for what is going on there. Well, that capital K is this, it behaves just like him. If you take this guy, if you take this guy right here, the whole thing, 4K, capital Q, small q, over A cubed, and you're dealing with that one, it's a constant, and you take this guy and you displace him. The more you're displacing him, the more force you have to exert. It's like pulling a bow and arrow. It's like pulling a bow. You've got an arrow in there and you pull the bow and you say, okay, what am I doing? Yeah, that's all the work I did. Okay, energy's conserved. Okay, there's not going to be any dissipation or anything. Okay, where it is, all that energy I did. All that energy I put into it is in the bow. This guy helps the bow work. You move it X, okay, let it go. Once you let it go, right when it goes through the equilibrium position, and it will, right when it goes through the equilibrium position, because it's being hampered. I get that it's being hampered. We all get that. But all of that work that you did is being brought right back. Yeah, but it's not being brought back to zero because you never pull a bow and arrow and then let go and you're hoping it just stops right there. All the energy that you worked, all the work that you did to pull the bow and arrow, all that work's going to manifest itself. All of that potential energy, all of that energy that you did, all that work that you did, it's stored as potential energy. All that potential energy is going to become kinetic energy at the place where it allows maximum potential energy. And that's right at the beginning. Here it started at zero. You did all this work to get to here. When it goes through there, all that potential energy, all that work that you did is manifested as kinetic energy. All that kinetic energy is going to go back into potential energy. It's not going to go any further. It's just going to go X away. That's huge. That's of huge significance. So it looks good to me. Absolutely looks good. So we look at it. We've got this. We'll just put the stuff, we'll put everything in there that's got to be put in there. I mean, KS, we're saying this is going to be your, I don't want to say, it behaves like it's a spring. This thing right here behaves like it's a spring. Behaves like it's a spring. I agree. Let's put in the numbers, and I think we're going to get the answer we want. Omega equals this. And they wanted the angular frequency, which is radians per second, not cycles per second, which is 2 pi times more than that. Cycles, forgive me, it's 2 pi, omega divided by 2 pi will give you the cycles per second. Omega divided by 2 pi. So they're saying here, okay, well, please do this. Well, let's go. Square root of. Here it goes. KS is this. We just said what KS was. The negative is just the bookkeeping at the end of it. The positive number, and then we throw the negative for the bookkeeping that's going on. So just this. 4K capital Q small q over A squared divided by M. 4K capital Q, 4K, capital Q, small q, over A squared times M. Or over A cubed times M, rather. I'm sorry. Fascinating problem. You know, it forces us. It forces us to do a lot of stuff, you guys. It forces us to believe forces us to really believe the assumption they gave you. The assumption's a given. X is very much less than A. Okay, then there's assumptions we can make, and we do it, and we got this answer. And that's how they wrote it. They wrote a different. The book allows you to write. The way they write it in the book, they have it like sideways a bit, but we know what that means. It's the same thing. Okay, we'll talk again soon about some other stuff. Thank you for your time.